So in this class we will discuss about ionic crystals. So as you already know, ionic crystals are made up of positive and negative ions. The ionic bond results from the electrostatic interaction between oppositely charged ions, that is positive and negative ions. Two common crystal structures found for ionic crystals are sodium chloride and cesium chloride structure. The electronic configuration of all ions of a simple ionic crystal corresponds to a closed electronic shells as in inert gas atoms. In inert gas atoms, the octet is complete and so the electronic configuration of the ions is similar to that of this octet or inert gas crystals. In lithium fluoride, the configuration of the neutral atoms are for lithium it is 1s to 2s1 and for fluorine it is 1s to 2s2 and 2p5. The singly charged ions have the configuration Li plus. After losing one electron from the outermost shell it becomes 1s2, so that Li plus, and Fi minus is by receiving one electron from the lithium, so the outermost shell become 2p6, 1s2, 2s2 and 2p6. As for helium and neon. Now, the electron gas atoms have closed shells and the charge distributions are spherically symmetric. We expect that the charge distributions on each ion in an ionic crystal will have approximately spherical symmetry with some distortion near the region of contact with neighboring atoms. So just like the inert gas systems, the electronic or the charge distributions are spherically symmetric in ionic crystals. Approximately spherical symmetry with some distortions near the region of contact with neighboring atoms. The distance between a positive ion and the nearest negative ion in crystalline sodium chloride is 2.81 into 10 to the power minus 8 centimeter, and the attractive Coulomb part of the potential energy of the two ions by themselves is 5.1 electron volt. Experimental value is 7.9 electron volt per molecular unit for lattice energy of crystalline sodium chloride with respect to separated sodium and chlorine ions. Sodium atom plus this ionization energy of 5.14 electron will give you sodium gas, and this chlorine gas with electron will give you chlorine gas plus this much of electron affinity or energy, and sodium plus chlorine will give you plus 7.9 electron volt cohesive. Electrostatic or Midline energy. The long-range interaction between ions with charge plus or minus Q is the electrostatic interaction plus or minus Q square by R. Attractive between ions of opposite charge and repulsive between ions of same charge. So the long range interaction with opposite charges or with the ions is the electrostatic interaction, which can be of the form plus or minus Q square by R, and this will be attractive if the charges are opposite in sign and will be repulsive if they are same in charge. The ions arrange themselves in whatever crystal structure gives the strongest attractive interaction compatible with the repulsive interaction at short distances between ion cores. So the crystal structure is favorable for interaction which are strongest attractive compared to the repulsive interaction. Okay, the repulsive interaction between ions with inert gas configuration are similar to those between inert gas atoms. So we can say that the interaction between ions which having an inert gas configuration are similar to those between inert gas atoms. The van der Waals part of the attractive interaction in ionic crystals make a relatively small contribution to the cohesive energy in ionic crystals of the order of 1 or 2%. The main contribution to the binding energy of ionic crystal is electrostatic and is called Midline energy. So the ions which having inert gas configurations have repulsive interaction similar to those of van der Waals interaction, but van der Waals part of attractive interaction in ionic crystal is relatively very small, and the main contribution of the binding energy in ionic crystal is from electrostatic interaction between the charges, and this is called the Midline energy. If Uij is the interaction energy between ions I and J, we define a sum Ui which includes all interactions involving the ion I. If we are representing the interaction between the ions I and J by Uij, then we can write Ui is equal to summation over J Uij, where the summation includes all ions except J is equal to I. Here I not equal to J. Okay. That's why we are not including a 1 by 2 here. Here the case is for I not equal to J. All the cases except for I equal to J. We suppose that Uij may be written as the sum of a central field repulsive potential of the form lambda exponential of minus r by rho, where lambda and rho are empirical parameters and a Coulomb potential plus or minus q square by r. So this we suppose that this interaction energy Uig can be represented as a central field repulsive potential and a Coulomb potential, and this will have these forms. So this represents the central field repulsive potential, and this represents the Coulomb potential. Okay, so we can represent the energy as the sum of these two, where the plus sign is for like charges, and the minus sign for unlike charges. Then unlike charges means Q and Q will give you Q square, so plus and plus will give you plus value, plus and minus will give you negative value, and so on. In SI unit, the Coulomb interaction is Q square by 4 pi epsilon 0 into R. The repulsive term describes the fact that each ion resists overlap with the electron distribution of neighboring ions. So here the repulsive interaction describes that each ion resists overlap with the electron distribution of the neighboring ions. We treat the strength lambda and range rho as constants to be determined from observed values of the lattice constants and compressibility. We have used the exponential form of the empirical repulsive potential rather than the r to the power minus 12 form used for the inert gas. In the inert gas crystals, we have used an r raised to minus 12 form for representing the repulsive potential, but we have here used an exponential form. Here exponential minus Rij by rho form. The change is because it may give a better representation of the repulsive interaction. For ions, we do not have gas phase data available to permit the independent determination of lambda and rho. We note that rho is a measure of the range of the repulsive interaction. When R is equal to rho, the repulsive interaction reduced to 1 by E times of the value at R is equal to 0. So this is clear from this equation. So when R is equal to rho, this range of interaction is reduced to 1 by E times of its initial value. 1 by E times that of the value at R is equal to 0. So in the sodium chloride structure, the value of Ui does not depend on whether reference ion I is a positive or negative ion. The sum of this equation, that is sum in this equation, the sum in this equation can be arranged to converge rapidly, so that its value will not depend on the site of the reference ion in the crystal, as long as it is not near the surface. So the reference, the sign of the reference ion is not an important factor here. The sum can be arranged to converge rapidly. Okay, we neglect surface effects and write the total lattice energy U total of a crystal composed of n molecules or 2n ions as U total is equal to n U into E. If this crystal consists of n number of atoms, n molecules, we can represent the U total as n into Ui. Here n rather than 2n occurs because we must count each pair of interaction only once for each bond only once, because since there are 2n ions, although there are 2n ions, here we have taken n for this energy, because this is because we must count each pair of interaction only once, or each bond only once. That's why if we take it twice, it will be double the actual value. Total lattice energy is defined as the energy required to separate the crystal into individual ions at an infinite distance apart. Convenient to introduce quantities Pij such that Rij is equal to Pij into R, where R is the nearest neighbor separation in the crystal. If we include nearest neighbor repulsive interaction only, we have Uij is equal to lambda exponential of minus R by rho minus Q square by R for nearest neighbors, and plus or minus 1 by Pij Q square by R otherwise. So we are defining a new quantity Rij as Pij into R, where a capital R represents the nearest neighbor separation. Okay, so we can define the potential or the potential energy as lambda into these two cases for nearest neighbors, and otherwise it is like this. So the U total, which is n into Ui, can be represented as n into Z lambda of e to the power minus r by rho minus alpha q square by r. Okay, where Z is the number of nearest neighbors of any ion, and alpha, which is equivalent to summation over J plus or minus Paj, which is known as the Midline Constant, which have to be evaluated. So the total energy can be represented by this, including the total number of atoms or interactions possible. So this will become in this form, where Z and alpha defined as here. The plus or minus sign is just as for previous reason that we have described before. At the equilibrium separation, what will happen? This change of U with respect to R will be 0, so that we can write N du by N into du by dr is equal to 0. So N into du by dr will obtain from this equation after differentiating this equation with respect to R. So we will obtain this equation after differentiating, and it is equal to R at equilibrium, is equal to 0 at equilibrium. And from this expression we will get, so we can represent R is equal to R0 at equilibrium. So after rearranging this, we will get R0 into exponential of minus R0 by rho as rho alpha q square by Z alpha. This determines the equilibrium separation R0 if the parameter rho lambda of the repulsive interactions are known. For SI unit, replace q square by q square by 4 pi epsilon 0. The total lattice energy of the crystal of 2n ions at their equilibrium separation R0 may be written using 20 and 20. 20 and 23 means this equation, this is equation 20 and this is equation 23. So what we are doing is, we have the expression U total as this, and we are substituting for the exponential factor, exponential of minus R0 by rho from this equation. So exponential of minus R0 by rho becomes rho alpha q square by Z alpha by R0 square. I have shown it here. Here we have the total energy expression like this, and from this we will get exponential term, and we are substituting for exponential term in this expression. So this equation will become like this. We cannot cancel out this like this. We are taking the common term outside the bracket, and we will remain with this term minus n alpha q square by R0 into 1 minus rho by R0. The term minus n alpha q square by R0 is the Midline energy. We shall find that rho is of the order of 0.1 R0, so that the repulsive interaction has a very short range. Okay, so this term is the Midline energy, and I will find that rho is of the order of 0.1 R0. So that means repulsive interaction is a very short range. And we will evaluate the Midline constant now. We have to evaluate the Midline constant, which is represented by alpha, and the first calculation of the Coulomb energy constant alpha is made by Midline, and it is known as Midline constant alpha, which is by definition is summation over J plus or minus divided by Paj. For 20 means the energy equation, the total energy expression. This for this expression, to give a stable crystal, it is necessary that alpha be positive. That means then only the energy will be minimum in order to be the crystal to be constant. If we take the reference ion as negative charge, the plus sign will apply to positive ions and negative sign to negative ions. An equivalent definition is given by, so if we divide both sides of this equation by R, we will get alpha by R is equal to summation over J plus or minus RPij. RPij is nothing but small rij, which we have defined before. So where rij is the distance of the jth ion from the reference ion and r is the nearest neighbor distance. The value given for alpha will depend on whether it is defined in terms of the nearest neighbor distance r or in terms of lattice parameter a or in terms of some other relevant length. So it depends on these conditions, the value of alpha. So as an example, we will calculate the value of alpha. So we compute the Midline constant for an infinite line ions of alternating sign as in here. So we are considering a chain of ions which having alternating signs, and the separation is r for nearest neighbors. So this separation is r, this is 2r, and this is 3r, etc. So the Midline constants from the above expression can be written as alpha by r is equal to 2 into, this is our expression, so alpha by r 2 into, for the first case this 1 by r, and the next case is minus 1 by 2r, and for the other 1 by 3r, and so on. So the series will continue as long as the chain goes on. And from this we can write alpha is equal, so r is common in the denominator on both sides, so we can write alpha is equal to 2 into 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus etc. The factor 2 appears here because there are two ions, one to the right and to the left at equal distance rij. It is quite clear from this figure. So if this is the reference point, these two atoms are lying which are of same sign and same distance, but on the two sides of the atom. So this need not be treated twice. So if we count all these interaction, we have to put a 2 here. So that's the reason for putting 2 here. And we sum the series by the expansion. The series can be we have the logarithm series ln 1 plus x minus x over by 2 plus x cube by 3 minus etc. As the Midline constant for the one-dimensional chain, this chain can be represented as using this equation as 2 ln 2. Okay, that is this series is ln 1 plus 1. Okay, because in the part of x here appearing 1, so x is 1 here, so ln 1 plus 1 will give ln 2. So alpha is nothing but 2 ln 2. In three-dimensional, it is not possible to write down the successive term by a casual inspection. More important, the series will not converge unless the successive terms in the series are arranged so that the contributions from the positive and negative terms nearly cancel. Okay, so we in the three-dimensional case, this is not as simple as that in the two-dimensional case. Typical values of Midline constants based on unit charges and refer to the nearest neighbor distance r. Here it is given in the table. This is the structure and this is the Midline constant. For sodium chloride, this is 1.747565, and cesium chloride and Zincline, which is also known as zinc sulfide, is given here. The Midline and repulsive contributions to the binding of a potassium chloride crystal are shown here. So Midline and repulsive contributions are shown here. This is for sodium chloride. This is the repulsive energy graph. Repulsive energy. This is just as the graph that we have shown when we are discussing the inert gas systems. And this is the Midline energy. This is for potassium chloride crystal. So this is about ionic crystals. So we have described what are ionic crystals and its peculiarity, and the Midline energy and the evaluation of the Midline constants. That's all about ionic crystals.